Okay, so this is a joint work with Lyudmil, Maxim, and Tony, and it's about an enhancement of atoms where we would like to put some integral structures on them. Since, as you all know, atoms are based on the A-model quantum connection, the correct integral structure there requires this correction by the gamma class. So this is what the struggle is about, how to incorporate this correction by the gamma class into the theory of atoms. So I'm going to start with a review of the C-analytic case. And it's mostly for making things more palatable and intuitive and explaining where the ideas and the heuristics come from. Maybe that's a mistake because that's going to take quite a bit of time. But one thing that, so we would like to do it for atoms which are inherently not C-analytic, but non-Archimedean analytic. And so for this, you need a little bit of work to recast the objects that give you the integral structures, which are these perf zero shifts that Max already mentioned, into the non-Archimedean context. And the key to that is to find some kind of a de Rham model for them in the C-analytic case, which will make sense in the non-Archimedean analytic case. And it's all based on using the Fourier transform, so everything will be done in the Fourier duo picture. So I'll describe the Fourier duo description, give the Fourier duo description of these gamma-corrected integral structures in the C-analytic case and in the non-Archimedean case, and finally talk about the atoms. Okay, so what is a Z structure in the complex analytic case? So an F bundle is a complex analytic F bundle is just a bundle together with flat connection on a complex manifold across a complex disk. It's a Z2 graded homomorphic vector bundle. The connection is a connection which, as you know, has at most a second order pole at 0 in the disk direction and a first order pole at 0 in the disk direction in the variables along the base of the bundle, which is the F manifold. And the Z structure, it's a lattice, it's a local subsystem of, say, full rank free abelian groups. There is a very subtle condition, which really is what makes this non-commutative Hodge theory to work. And the condition is the compatibility between this lattice with the Stokes data for the connection in the U direction. And so that's the definition. And I'm not going to talk about the compatibility condition, but I'll say a little bit about it later on when we talk about the Fourier duo description. Okay, so one thing that you get from this datum is that the data actually extends automatically to the full complex line from the disk, and it gives you a bundle that's algebraic and a connection that's algebraic in the U direction. One thing you would like to have, which somehow I suppress here, and I'll mention how we'll deal with it later on, even though we don't want to dwell on it, is that you would like this integral structure to be a local system of finitely generated abelian groups, allowing for torsion, so that the image in H is a full lattice, but there could be some torsion. And so already this is not completely clear in the C-analytic context, because it's not clear how this torsion, what's the compatibility condition between this torsion and the Stokes data. But from the Fourier duo point of view, actually, there is a good good condition, and so you can actually allow for torsion. So I'll talk a little bit about this later. But the goal is how to define this Z structure on F bundles in the non-Archimedean setting, and in particular, how to remember something about this powerful and difficult compatibility condition. And the key difficulty in doing this is that these local systems and their compatibility with the Stokes data, in the C-analytic context, they require the Riemann-Hilbert correspondence. And that's what we're missing in the non-Archimedean setting. There is unfortunately no Riemann-Hilbert correspondence for non-Archimedean flat bundles in equal characteristic. Very recently, people were able to actually construct a full version of the Riemann-Hilbert correspondence for flat bundles in the non-Archimedean case in the mixed characteristic situation. But it's very complicated and requires this ring or field of periodic periods, Fontaine, and this doesn't quite transplant to the equal characteristic case. So you need to do something else. Okay. So now the first step is to take this data that we were talking about and pipe it through the Fourier transform. And on the other side of the Fourier transform, we can see how the data looks like and modify it a little bit so that it will be something that makes sense in the non-Archimedean setting. So if you do the U-direction Fourier Laplace transform of this connection, you get a new object. It's a regular holonomic D module on B cross P1 with a dual variable Z. The singularities of this D module are B cross infinity, as we expect, and there is also a spectral cover. So there is a singular locus which is embedded in B cross the line, affine line in Z, and it is disjoint from the section at infinity. You know, if you think about this D module as the Gauss-Manin system, in the case when you have a mirror, Landau-Ginzburg mirror, the way Max was talking about at the beginning of his talk this afternoon, this will be the cover that traces all the critical values of the Landau-Ginzburg potential. And there is a condition on this D module, which is this perf zero condition, or the D module version of the perf zero condition, which says that if you project, so first, of course, you want to say that if you restrict to infinity, you get 0, but also you want to say that if you project to the base, you get 0 again. So you have global cohomology 0 along P1. So that's in essence the perf zero condition. So this is what the Fourier dual F bundle looks like, and we'll modify it and make it simpler and simpler in a moment. So now the key to what we're doing is this. So as I said, the Riemann-Hilbert correspondence, which in the C-analytic case we know what it does. It converts regular holonomic D modules, for example, Fourier dual F bundles, to perverse sheaves. And the perverse sheaves that correspond to the Fourier dual F bundles are not arbitrary, but are these perf zero perverse sheaves. And since we've been talking about that without saying what they are, let me very quickly say what they are. These are perverse sheaves on the complex line with vanishing cohomology. So you can say that perverse shifts on the complex line with vanishing cohomology. It's a category. It's a very interesting and rich category. It's a Tanakian category. It has convolution, which is just the, sorry, it has a tensor structure, which is the convolution of perverse shifts on the line for the addition. And it has a fiber functor, which is the nearby cycles at infinity. And it's a neutral Tanakian category, which is kind of a Betti version of the category of exponential motives. It has several different descriptions which are useful, and actually has one more that I'm gonna explain later, which is this de Rham description, which is what you need for the non-Archimedean setting. So you can say, instead of saying perverse shifts, you can say constructible shifts. So they're not actually complexes. They are complexes, but they're supported in one homological degree, which happens to be -1, but let's say constructible shifts. So constructible shifts on the line with global cohomology, 0. And they're also representations of a quiver. The quiver is a full quiver with n vertices, n square minus n arrows connecting all pairs of distinct vertices, and one loop at each vertex. Sorry, 2 loops at each vertex with the only relation saying that the 2 loops at each vertex are inverses to each other. So this is this category perv 0. And there are variants. You can take constructible shifts with complex coefficients rather than rational coefficients. But interestingly, perverse shifts in general don't make sense for constructible complexes of, say, finitely generated abelian groups, because Verdier duality doesn't work. But this perv 0 thing actually does make sense because it's given by a vanishing of cohomology condition. So I can say that a perv 0 constructible complex of finitely generated abelian groups is just a constructible shift of finitely generated abelian groups with vanishing global cohomology. So that could include torsion. And the quiver description still works in this case. And in fact, you can check that if it works, it works. It works modulo torsion. So I'll maybe mention something about it later. But anyway, so this Fourier dual F bundles in the C-analytic case are just families of perverse shifts or constructible shifts, if you want, on B cross C that are in perv 0 along the CZ direction. Okay, now you can say what a Z structure is. It's a pair. In the Fourier dual picture, it's a pair of a constructible shift of finitely generated abelian groups, an isomorphism of the corresponding regular holonomic D module with M, such that the singular locus of M of the integral guy is S, what was the singular locus of M, and also it's in perv 0. And I already made this remark, but let me make it again. If you have this structure on the Fourier dual F bundle, then if you mod it out by torsion, it's also a Z structure. So it also satisfies the perv 0 condition. So, so adding the torsion in this way has more information, but doesn't destroy the property of the thing being a Z structure. Okay. Now, there are several things that you can do with this. One is that you can specify this Fourier dual F bundle by specifying data at a point, at the general point of B and near infinity on the projective line. So if you take the discriminant divisor for the spectral cover, so it's the branch divisor for the reduced spectral cover, and you take any point in that, and you take a small disk near infinity, then you get a confined version of this structure. So a confined version will be a constructible sheaf of finitely generated abelian group and an isomorphism, which is exactly what we were saying before, but only happening on this small locus. So at the fixed point B and in this small disk near infinity. So it's actually a local system of finitely generated abelian groups on the punctured disk near infinity, an isomorphism of the associated D module on the punctured disk near infinity with M restricted at the point, and an isomorphism such that at the point B, it extends to an object in perf 0 on the whole line, and the isomorphism extends to an isomorphism of the associated D modules, but only at one single point where we have the spectral cover being unramified. So this is a confined torsion-free Z structure, and in the C-analytic case, isomonodromy actually gives you bijection between torsion-free Z structures and confined torsion-free Z structures. So you can only, because you have analytic continuation and isomonodromy. So you can just work with the confined guys, which are much easier. They happen at one point and just on the line. I mean, on a small disk, actually, in the line. It's a disk near infinity. And if you have a Z structure on a framed F bundle, so that means H is trivialized, this gives rise to a confined Z structure on the Fourier transform. Compatibility with Stokes data now can be formulated in the Fourier dual picture. And it's just equivalent to the first condition in the definition of the confined structure. The fact that the integral structure that you have specified near infinity extends to an integral structure on the whole line. So in the C-analytic context, it just says that the integral structure we specified near infinity is preserved by the global monodromy for the Fourier dual F bundle. So that's because everything is regular now. That's a much easier condition to state and check than the compatibility with Stokes data. And this, by the way, can be made precise and rigorous in the non-Archimedean context, and that's what we are going to be doing. Okay, now this was just the general theory of F bundles, Fourier dual F bundles, and Z structures on them. Now let's focus on the ones that we really want to understand, which are the quantum connections, the A model F bundles. So suppose that we have a smooth projective variety, an ample class. H is the global cohomology of X. B is going to be, so I'm going to look right now, just for simplicity of the discussion, at the small base, at the just a one parameter base going in the direction of omega. And so we take the trivial bundle with fiber H, the usual quantum connection, which is given by basically three operators, K, G, and A, where K and A depend on Q analytically, or formally, or let's say analytically, and G is actually constant. But they don't depend on U. It's the key thing. And so one great feature of this situation is that if you look at the large volume limit of this quantum connection, so replace the quantum multiplication by the first-order class and by the symplectic form by the classical multiplication, then you get another F bundle, like a classical F bundle. And the relationship between this and the quantum one is actually very interesting. So first of all, this G, which is constant, is the grading operator. It's semi-simple. It has eigenvalues which are half integers, at most half integers. And the classical cup product with the first-order class is nilpotent. And of course, these are the leading terms in the series A and K viewed as series of Q. Now, what is the Z structure? Conjecturally, so this is the story that we proposed in the old Hodge theory paper. Assuming that the quantum product converges as Q goes to 0, you can look at a function in Q and U with values in H, so a section in our bundle. You can restrict that section to a sector which is the product of the positive real lines sitting inside CQ and CU. And if you have a horizontal section for our connection on this sector, then we can gauge transform that section by the exponent of U inverse log Q times the classical A, and take the limit where Q goes to 0, and this limit is well defined and set it, and it's flat with respect to the classical connection. And then you can gauge transform that flat section. So you started with a flat section of the original quantum D module. You took a gauge limit of that flat section, you get a flat section in the classical D module. And you can gauge transform that again, and you get a section which is actually constant. And that allows you to define a Z, a local system of 3 abelian subgroups inside the quantum D module. And here it is. These are, it's given by flat sections of the quantum D module such that this psi constant guy that I defined on the previous page belongs to a lattice. And that lattice is essentially the Z lattice in the cohomology of X. It's moved by two linear operators. One is just a multiplication by 2 pi I in some power on each cohomology degree. And the other, it's a multiplication by a characteristic class, which is this gamma class, which is written right here. So it's the exponent of the Euler constant multiplication by the first-order class of X. And then, oh, I'm missing a sign. I think there is a -1 to the n here. And then the zeta of n over n times the n-Chern class of n. And there is a -1 to the n there. So we define this Z structure on H, and the conjecture is that it is this structure on the quantum D module viewed as an F bundle, meaning it's compatible with the Stokes data. So I should say this is what we call gamma conjecture, and there is something else that's called gamma conjecture in the literature, which is much stronger and only makes sense for Fanos. This makes sense for any projective manifold, actually, or any symplectic manifold, in fact. Okay, so our problem was to find some analytic and Fourier dual description of this gamma head corrected Z structure and make it work in the non-Archimedean setting. Okay, so here is the strategy we are going to employ. So first, we are going to define this structure on the classical limit of the D module, the quantum D module. Then, here is something really interesting happening. The quantum D module actually is gauge equivalent to the classical D module near infinity in U. So we want to construct this gauge equivalence. And another interesting thing that's happening is that the quantum D module near U equals infinity is gauge equivalent to its Fourier dual near Z equals infinity. So there are two gauge equivalences which allow you to take the Fourier dual Z module near infinity and think about it as the classical limit of the quantum D module. And because we'll have the gamma head corrected Z structure on the classical limit, then we'll get something near infinity on the Fourier dual guy. And then, yeah, so we transfer the Z structure from step 1 to the Fourier dual guy. And of course, we want to do this in the non-Archimedean setting, which requires some work. And then, of course, so you define it near infinity, so you need to say that it extends to the whole line, which, remember, makes sense on the Fourier dual picture, and it is the compatibility with Stokes data, and it will make sense in the non-Archimedean setting. And then you need to say that this guy that you've constructed at the end is compatible with both of the compositions, which would say that this gamma-corrected Z structure defined in the Fourier dual picture induces a Z structure on atoms. Okay, so the first thing we do for steps 1 and 2 is to show that there is a canonical gauge equivalence between the quantum connection and its classical limit in the neighborhood of infinity. And this guy is uniquely determined as a solution of an analytic ODE, and the same ODE makes sense in the non-Archimedean setting, so it also works in the non-Archimedean setting. Unfortunately, it's not quite explicit. I mean, you know it's there because it's a unique solution of an ODE, but it would be good to have a formula for it. But in some sense, there is a formula for it, but it's messy. So we go around that in a different way. But this actually gives you a slightly better description of this formulation of this gamma conjecture. So you can look at the gauge transformation, which is multiplication by or conjugation by u to the g on the even part of our bundle and u to the g plus 1/2 on the odd part. So this is, you know, the grading. The grading is integral on the even part and half integral on the odd part. So this g plus 1/2 corrects the half integral grading. And then there is a flat connection, which is the gauge transformation with respect to that of the classical connection. And its monodromy around infinity is multiplication by the Chen character of the canonical class on the even part and minus the Chen character of the canonical class on the odd part. The monodromy around Q equals 0 is multiplication by omega. This is all classical multiplication. And the monodromy preserves the image of the topological K theory multiplied by any invertible class in the even cohomology. In particular, the image multiplied by the gamma class or by the constants that we use the powers of 2 pi I. So it preserves this guy, the image of the topological K theory in H, multiplied by the constants, multiplied by the gamma class. And the gamma hat corrected integral structure is defined this way, and a better formulation of the conjecture from whatever, 15, 20 years ago is that if you move this lattice, the gamma hat corrected image of the cohomological K theory by these two gauge transformations, this is compatible with the Stokes data. Okay. Now, this takes care of this first and second step. We get a gamma-corrected integral structure in the classical limit, or maybe slightly massaged classical limit. And we wrote a gauge transformation between this classical limit and the quantum connection near infinity. So we got this structure there, and the conjecture is it's compatible with the Stokes data. Now, for step 3, comparing with the Fourier duo, we need to really look at the Fourier transform. So if you have, again, a framed C-analytic F-bundle, yeah, I'm going to write it uniformly so that I don't care about the degree 2 cohomology classes and higher degree cohomology classes. So it looks like this, the quantum connection. And so you just need to remember that the AIs could have first order poles in the coordinates TIs, or could be homomorphic if they're of degree 2. And, sorry, the other way around. They have first order poles if they're of degree 2, or could be homomorphic if they're of higher degree. And Fourier transform is a D-module where the module is just H tensor Laurent polynomials in U with the action of Z and dZ given by the connection acting with U squared du or U inverse. So it converts this D module, this connection to a D module, which, as we said, is regular holonomic. And away from the spectral cover, the spectrum of K plus infinity, it's a logarithmic flat bundle. Right? It's smooth there. Unfortunately, on the nose, this logarithmic flat bundle is not trivialized. But you can trivialize it, but there is some resonance that you have to worry about. So you can choose an integer so that if you take the spectrum of G and shift it by that integer, it doesn't contain anything negative. And if you choose an integer like that, then you can trivialize the F bundle, the D module. So you get an actual F bundle where the fiber is, again, H. So it's a trivial bundle with fiber H. But now the Fourier duo action of the differential operators, or the Fourier duo quantum connection, which depends on the choice of that integer, is given by slightly more complicated operators. G plus L0 minus 1 times K minus Z inverted, and G plus L0 minus 1 times K minus Z inverted times AI. And outside of the spectral cover, in particular near Z equals infinity, it doesn't, these connections, even though they look different, they're gauge equivalent when you shift the L0. So once you found one L0 that shifted the spectrum correctly, anything bigger will work as well. And there are canonical transformations between those. Okay. Now, let's identify the basis of the original wave bundle and the Fourier dual one in the most if possible way. So we keep B the same, and we say U equals Z. Then if you pull back this Fourier transform F bundle, you just get H. And the theorem is that the original quantum connection and the Fourier transform quantum connection under this identification of the basis are gauge equivalent, canonically. So here is a formula of the gauge equivalence. So there are some operators that we call Fn. They depend on G plus L0 and K. Then there is the gamma function evaluated on G plus L0 and a series. And we conjugate with this, and that relates the original quantum connection with its Fourier transform. This is near U equals Z equals infinity, in a small disk near there. And so you see, the connections, they look very different, but they're gauge equivalent. And what these operators Fn are, they're actually values of some canonical analytic functions in n variables, or n plus 1 variables, where you evaluate a function on two operators by starting with a monomial and evaluating the monomial on an operator this way. So you evaluate the monomial on the first operator, and you insert the second operator between each two powers. And then take the limit. And these classical canonical functions, there is a formula for them. So there are sums of ratios of gamma functions times some rational functions, which are defined this way. So the point is that there is some completely explicit gauge equivalence between the original quantum connection and its Fourier transform near infinity. Now take theta to be that gauge equivalence, and transport the gamma conjecture from the original quantum connection to the Fourier dual side. So what it says is, it says that if you take the lattice the way we defined it before, phi inverse, psi inverse acting on the gamma class corrected lattice, and you move it by theta, then that extends on the whole line, at least away from the spectral cover. And so in particular, confines the structure on M. That was the extension condition. So this is the gamma conjecture, and in this complex analytic setting, it's now entirely formulated on the Fourier dual side for a regular holonomic D modules. There is no mentioning of Stokes data here, but it's equivalent. So this completes the step 4 of the strategy, and now we have to go to the non-Archimedean setting. And how am I doing with time? Oh, not bad. Okay. Now, in order to do that, we need to be talking about extendability with some perf zero property and compatible with gamma structures. And it turns out that mirror symmetry is actually very useful here, because these guys, whatever they are, they should come as some data that's associated with the exponential motive that's associated with the mirror. As Max was saying, the mirror is not really a Landau-Ginzburg model in general, especially when we look at the full base, but it's some family of non-commutative Landau-Ginzburg models, family of categories. So we don't quite know that these motifs are there, but if we had a good theory of exponential motifs for those categories, then most of the conjectural pieces in this story that I'll describe will not be conjectural, they'll be just there. So suppose that you have a smooth projective variety over the complex numbers. Look at the cohomology. So we have a bunch of linear operators. We have the grading operator. We have the multiplication by the Chern classes of the tangent bundle. We also have the multiplication by the first Chern classes of line bundles. In particular, I can choose a basis of the Nero-Severi group and say a fractional Nero-Severi group, but an integral basis, and take the first Chern classes of those guys. So these are operators. And using these operators, we can actually construct some very interesting object. We can construct an algebraic flat bundle defined over the rationals. So the base is going to be a torus. It's going to have dimension the rank of the Nero-Severi group plus 1. And say the coordinate in the Nero-Severi direction is going to be qi, and the coordinate in the extra direction will be miz. We'll have a trivial bundle on top of that. There will be a connection, which looks like the classical connection we discussed before. It's a product with the first Chern class of X and the first Chern classes of these line bundles that generate the Nero-Severi group. So this is like a small classical cohomology D module, only along H2. And this thing has two filtrations. It has a Hodge filtration, which is given by the G grading being less than or equal to K, and has a weight filtration, which is given by the G grading being greater than or equal to R. And the weight filtration is horizontal with respect to nabla, and the Hodge filtration satisfies Griffith's transversality. And notice that by accident of the construction, some miracle happened here. The weight and the Hodge filtration by themselves are opposed here. You don't need a complex conjugate of the Hodge filtration. But if you put a rational structure or a Z structure, and I'm going to put it this way, so I'm going to move the Z lattice by the 2 pi i's, and then we're going to move it by a class that looks very much like the class that we used for the gamma class. Remember, this piece was the gamma class. And instead of multiplying by C1 times the Euler constant, we'll multiply by log Z. And also we have stuff that's going in the Q direction, which is just the multiplication by Q to the C1 to the C1 of Li. So this structure is horizontal with respect to the connection, and complex conjugated with respect to the corresponding real structure gives you complex conjugate Hodge filtration, and you get an admissible variation of integral Hodge structures, mixed Hodge structures. So just starting with this projective variety and a little bit of data, which is the choice of a basis in the Nero-Severi group, you got an integral variation of admissible Hodge structures defined over the rationals over the torus, just from the symplectic geometry. In fact, in this case, it's just the classical multiplication. And so the observation is that it's not just an admissible variation of Hodge structures, but it's of Tate type. So the pure pieces are Tate Hodge structures. It's motivic. So it's of geometric origin. It's a realization of a family of mixed state motifs parameterized by this torus. And it's defined over the rationals. So this is somehow the main virtue of this correction of the gamma class. That's what makes this thing motivic, because the motivic Galois group of Tate motifs is given by polylogarithms, some exponential of a freely algebra generated by polylogarithms, multiple zeta values. And here we just added zeta values. So they're just the x1s in the motivic Galois group of Tate motifs. Okay, now we want to use this somehow to say what the Z structure is in the non-Archimedean context. So take the non-Archimedean field to be Q is series with coefficients in Q bar. Take the Fourier transformed A model F bundle. And so I wrote down what it is. Now separating in the B direction, separating the directions that have pole and the directions that do not have pole. And you can extend the connection D that I wrote. So there were no T's in the connection D. It was only on the small part of the Frobenius manifold. But you can extend it everywhere trivially. Sorry, this is a typo. It should be no TJ here. It's just the trivial connection in the T direction. You can check that these two guys are gauge equivalent near T equals 0. Q equals T, Q equals 0. So the gauge equivalence is the same one we used in the classical case. Okay, now there is a canonical formal gauge transformation. So F depending on G plus L0 and K, which transforms one into the other. And it's actually convergent in the non-Archimedean case. On a polydisk near 0 in the QIs, on the whole vector space of the T's, and a small annulus in Z centered near infinity. So this F guy, this gauge transformation is a composition of that, of the theta and the phi that we had before. And in fact, there is a formula for this one, but I didn't write it. What happened? Where am I going? Yeah, so there is some universal series with rational coefficients that gives this gauge transformation. And one thing to worry about, and it in fact you really need to fight with it when you're defining the Z structure, is that the radii of this annuli in Z, they depend on Q. And they depend on Q in such a way that, of course, the annuli are far away from the spectral cover. But they don't depend on T. Now choose a point with coordinates Qj, Qi, Tj, so that the Euler vector field has a maximal number of eigenvalues at that point. So they're, as I said, away from this annuli, so they're less than 1 minus epsilon q by norm. And you can choose small radii so that the annuli around the eigenvalues and these big annulus around infinity, they're nested. They don't intersect. So I'm calling this nested system of annuli nest Qt. And our quantum connection, the Fourier transform quantum connection, is defined everywhere outside of infinity and the spectral cover. So in particular, it's defined on this nest guy, this union of annuli. On the outside annulus, on the big one, the one near infinity, it's actually analytically isomorphic to this variation of Tate-Hodge structures that we constructed by using just classical linear algebra. And you can base change it to K. You can base change the filtrations, the Hodge filtration and the weight filtration, and you get this standard Tate variation of mixed Hodge structures defined over K now on that big annulus. And now you can formulate the Fourier dual non-Archimedean version of the gamma conjecture. You want to say that on the affine line cross GM over Q bar, there is a family of mixed motifs such that they have singularities at most at the leading coefficients of the eigenvalues. So I didn't say this, but so if you look at the eigenvalues, the spectral cover, right? We are at one point. So if you look at the fiber of the spectral cover, the eigenvalues at one point, the different eigenvalues, they begin with some term in the Puiseux series. So this is the first term in the Puiseux series. So it has some coefficient which is in Q bar, and it has some exponent which is in Q. So the singularities of this Q bar family of mixed motifs should be at most at the coefficients. Of course, you know, you can move them around by scales. The nearby fiber at infinity should be a variation of mixed state motifs whose Deran version is exactly the canonical variation that we wrote from linear algebra classically, and whose Betti version is the gamma lattice near infinity that we defined. And if you base change everything to the non-Archimedean field, then you want to say that this isomorphism between the nearby cycles and the variation of Tate mixed Hodge structures is induced from a global isomorphism on all of the annuli, on the whole system of annuli. So it's only on the big annulus to start with, but now you would require it to be on all annuli, where on the small annuli you just put the Fourier dual F bundle. So this is the way the gamma conjecture looks like at a single point. It only sees the leading term in the eigenvalues. And now you want to allow the points to vary in the Frobenius manifold minus the branch divisor for the spectral cover. So if you take the manifold minus the branch divisor of the spectral cover, it maps to the configuration space of points in the affine line given by the eigenvalues of the Euler vector field at that point. But the configuration space of points, if say the k points in the configuration space of points in the non-Archimedean affine line, they're stratified. They're stratified by trees. Okay, do I have time to explain that? Maybe very quickly. So you know, the Berkowitz affine line is a rooted tree. The k points are just certain leaves in that rooted tree. In particular, the spectrum of k will be certain leaves in that rooted tree. And the convex hull of 2 or more leaves is a finite subtree. So if you take just a configuration of leaves, that gives you a particular finite subtree, and so you can look at all configurations for which that finite subtree is the same. So this is roughly the picture. You have this rooted tree where the root is this G, the Gauss point. Lambda 1, lambda 2, and lambda 3 are certain leaves. And you look at all the configuration of leaves, which are eigenvalues, such that they have 3 convex hull, a given finite tree. And so you get this certification by point configurations of type T. And there is a map from point configurations of type T to point configurations of type T of smaller degree, where the smaller degree is the number of descendants of a given vertex in the tree. And the projection of the image of B minus the discriminant to one of these smaller degree guys is an equivariant algebraic subvariety for the action of dilations and translations on the line. And so the conjecture is that for every tree and every vertex, we have an invariant variation of mixed motifs, invariant for the action of the dilations and translations on this subvariety across the affine line. At the leaves, the leaves that correspond to the eigenvalues, the variation is the one that satisfies the property from the previous conjecture about the nearby cycles at infinity being the Tate variation of Hodge structure. And for every descendant of V, we have that the corresponding analog of the perf zero sheaf is glued to its counterpart for the vertex V. So they're isomorphic. I am actually out of time, so I'm probably not, I'm out of time. So I'm not going to explain. So for this, you need this Deran version of perf zero, which makes sense in the analytic case. You need to say what it is. I just wrote some letters to say that it exists, but didn't explain. But I'm not going to explain it, so I'm going to stop here.